So let's look at page 3. So this is where we're going to start to write our electron configurations. There's 3 types of electron configurations that we're going to learn how to write. We're going to learn how to write what's called a full electron configuration, which we're going to do on this page. We're going to learn how to write orbital box diagrams, which will be on the next page. And then the second type that we're going to learn to write on this page is called a noble gas notation. And so the full and the noble gas kind of go hand in hand, so we'll do both of those on this page. And one of the things we want to do is also relate it to the periodic table. But there is a filling order that we talked about, kind of established on page 2. You can see at the top of the page here, you'll always have access to this. And so what you need to bring to bear to do these configurations is knowing the maximum number of electrons per subshell. See if I can't write that a little bit better. So for a particular type of subshell, and again, we're only going to go through 6s, so we don't have to deal with the F subshells. We're going to try to figure out the maximum number of electrons. And so what we saw on page 1 is S's hold 2, P's can hold up to 6 in their 3 orbitals, D's can hold up to 10 electrons in their 5 orbitals. And so the idea here is you're going to go to the periodic table for a particular element, in this case neon, and you're going to look up how many electrons it has, right, based on its atomic number. We're dealing with atoms. And you're going to follow the filling order and fill up each subshell as you get to them. And so the first subshell that you always get to is the 1s. And the 1s can hold 2 electrons. I have 2 electrons, so I'm going to fill it up, and that's going to leave me with 8 electrons. At that point, I go to the next available subshell, which is the 2s. It can hold up to 2 electrons. I have 2 electrons, so I fill it up, and that's going to leave me with 6 electrons. Then the next available subshell is the 2p. The 2p can hold up to 6 electrons. And so I have 6 electrons, so I can fill it up, and that takes care of my 10 electrons. And so there's the full electron configuration for neon, 1s2, 2s2, 2p6, where my red numbers here, my superscripted numbers, represent the number of electrons. It should total up to the number of electrons I'm trying to show. And so in this case, if I'm showing a neon atom, it should have 10 electrons. If we go down to our second element here, manganese, manganese has 25 electrons. And so I know I'm going to have at least 10, so I'm going to go ahead and put in my subshells here and work through those. So again, I'm going to come to the 1s, fill it up with 2. That'll get me to 23. My 2s can hold 2. That'll get me to 21. My 2p can hold 6. That'll get me to 15 electrons. And so now I'm going to do what I did before. I'm going to go to the next available subshell, 3s, which I know can hold 2 electrons. That gets me down to 13. Then I'm going to go to my next available subshell, which is the 3p, which can hold 6 electrons. And so that's going to get me down to 7 electrons. After the 3p comes the 4s, which, just like all the other s's, can hold 2 electrons. That gets me to 5 electrons. The next available subshell after the 4s is the 3d. Remember, the 3d comes after the 4s. That's just the way it is. And a d subshell can hold 10 electrons, but we only have 5 electrons left. So my last 5 electrons get dumped into the 3d. 3d is not filled, right? But that's kind of the goal, is to show 25 electrons. So let's move to chlorine. So chlorine has 17 electrons. And so just like the others, we know it's got more than 10, so I'm going to go ahead and put in the 3 subshells that gets us to neon. And so again, the 1s can hold 2, the 2s can hold 2, the 2p can hold 6, so that gets us to 15, 13, 7. And so now I'm going to come to the 3s, which can hold 2. And then I'm going to come to the 3p after that, And at that point, I have 5 electrons left, and my last 5 are going to go into the 3p. And what I want you to do is think about this in terms of the periodic table, right? When you look at the periodic table, you've got 2 columns. So these 2 columns is what we call the S block. Groups 3A through 8A, right? This is 6 columns wide. That's the P block. The transition metals, which is 10 columns wide, that's what we call the D block. And then the intertransition elements, that's the F block, right? This is 14 columns. And so we're not going to deal with the Fs in this particular class. And so when we look at chlorine, think about what's going on here, right? 1s, and sometimes it's probably best to think about helium sitting here sometimes, right? So if we think about what's going on here, 1s2 gets me across hydrogen and helium. Then I get down here to 2s2. Then I got to go 2p6 to get to neon. And then 3s2 gets me across sodium and magnesium. And then to get to chlorine from aluminum, I go 3p1, 3p2, 3p3, 3p4, 3p5. And so again, the periodic table matches the filling order of the electron structure. So we can kind of see that as we highlight our path to chlorine. And so if we think about cesium, it's down here, period 1, period 2, period 3, period 4, period 5. It's down here in period 6. It's in the S block, and it's in column 1, right? So again, this is kind of S1 column, S2 column. Over here we have P1, P2, P3, P4, P5, and then starting with neon, we have P6, right? Helium doesn't have a P6, it's just filled up with the 1s2. And so I bet you, based on its location in the periodic table, cesium is going to end in 6s. The 6 comes from the period it's in, the S comes from the block it's in, and I would say it's going to end in 6s1 based on the fact that it's in the first column of the S block. And so if I go ahead and fill in all of the subshells it takes to get to 6s, which is all of them from our filling order, right? You got to go through the 1s, and then the 2s and the 2p, then you got to go through the 3s and the 3p, the 4s, the 3d, the 4p, the 5s. I didn't give myself enough space here, or I took too much space. So the 3s, the 3p, the 4s, the 3d, the 4p, the 5s, the 4d, the 5p, right? If we kind of take our way through that, right, cesium has 55 electrons. I can put 2 there, that's 53. 2 there, that's 51. 6 there, 45. 2 there, 43. 6 there, 37. 2 into an S, that's 35. 10 into the 3D, so that gets me down to 25. 6 into the 4P, that gets me down to 19. 2, 17. 10 again, I'm down to 7. 5P, I can put 6 in. That leaves 1 electron, which I put in the 6s1. So if you can start to make the connection between the filling order and the periodic table, it's really going to help you feel comfortable with electron structure as a whole. Let's save antimony for a second. Let's go back and start talking about noble gas notation. And when you find the noble gases on the periodic table, right, they're over here in group 8A. And so helium is element 2, neon is 10, argon is 18, krypton is 36, xenon is 54. Those are the ones that we're going to worry about. And to get to those, right, to get to helium, notice there's a gap here, you fill up the 1s. To fill up neon, we can see in example 1, right, that's after you fill up the 2p. Argon's after you fill up the 3p. That gets you to 18 electrons. Filling up the 4p gets you to 36 electrons. That's where krypton falls in the filling order. If you fill up 5p, that gets you to xenon. That's 54 electrons. And so the noble gas notation is going to allow us to simply use a noble gas to represent all of the full shells, all of the electrons that get us to the end of a row. And so if we think about neon here, its valence shell, right? Again, this shows valence electrons. And so that's the outer shell. And that's going to differ from element to element. It's going to be equal to the period. And so for neon, that's shell 2. And so you can kind of see there's kind of a natural dividing line here where we're done with the first shell and we start the second shell. And the idea is we can use helium to represent 1s2. And then what we show after that is still 2s2, 2p6, right? So we're still showing 10 electrons. It's just the first 2 are represented as helium, and then we're showing the last 8 electrons as 2s2, 2p6. And what that allows us to do is to easily recognize the valence shell number, which in this case is 2, right? As well as the number of valence electrons, which in this case we'd add up the 2 and the 6. This is 8. And so valence shell number is going to be what period that element's in, what row on the periodic table, and number of valence electrons is going to be group number. And again, this is for the main group, right? The A columns. Maybe let's write that as 1A through 8A. So if we look at something like manganese, right? Manganese has 25 electrons. And so the noble gas that has the most electrons that's fewer than 25 is argon, right? Argon represents 18 electrons. So instead of writing out a configuration that shows all 25 electrons, now I only have to show 7 electrons because argon takes care of 18. The question is, where do you start after that? Well, if you have the full electron configuration, you can easily see that there's the gap between 3 and 4, right? You can also use the filling order and see that argon gets you to 3p. And then after that, you show 4s2 and 3d5. Notice on the periodic table that again, you start with argon. So that's just the brackets around argon gets you to there. And now, right, 4s2 gets you across potassium and calcium. There's your 4s2, and now 3d1 gets you to scandium, titanium is 2, 3d3 is vanadium, 3d4 is krypton, manganese is 3d5, right? So what we're showing in a noble gas notation is just what's in that row in terms of electrons where the element is. So let's look at chlorine and see if we can't make that case again, right? So when I look at chlorine on the periodic table, what I see is I've got, it's over here. I've got a box around it. It's in the 3rd period. So what I want to do is go up to the 2nd period, neon, and that's the noble gas I'm going to use. So I can use neon, which of course represents 10 electrons. I've got 17 total, but now I only have to show 7. And so I'm going to do that by showing 3s, in this case 2, 3p5. And so there's my noble gas notation for chlorine. And so if you can start to think about what we're doing, again, right, we're showing through neon. Neon represents 1s through 2p. Then we're just showing the outer electrons. And so what this tells us about chlorine is that the valence shell number is 3, and the number of valence electrons is equal to 7, right? 2 plus 5. And that makes sense because chlorine's in group 7a. It's a halogen. All the halogens have 7 valence electrons. Fluorine, chlorine, bromine, iodine. They all end in S2P5. It's just that based on what period they're in, it's going to tell you what the shell numbers in front of those subshells. So chlorine ends in 3s2, 3p5. So if we use that to our advantage with cesium, right, when we start looking at cesium, down here in group 6, what I want to do is go to the end of the previous period, which is period 5, and I can use xenon. And so for my 55 electrons, 54 of them are taken care of by xenon. I only have to show one more electron, which in this case I'm going to show as 6s1. Again, you're always going to start with the s for whatever period you're in. That's another way to kind of keep track of where you're at. And so if I want to do the noble gas notation for antimony, I find antimony on the periodic table. I go to the previous, let me go ahead and erase this circle here. So I go to the previous row, which is period 4, and I'm now going to put in krypton. That's 36 electrons, and now I'm just going to work my way across this period to get to antimony. So to get through rubidium and cesium, again, this is row 5, so this is 5s. I'm going to fill it up with 2 electrons. Now I'm going to work my way across yttrium, zirconium, all the way across to cadmium. That's the 4d. The d block is shifted down 1. And so I put 10 electrons in there. And now indium is 1, 10 is 2, antimony is 3 electrons into the 5p subshell. And so it's going to end in 5p3. And again, if we do the math here, antimony in total has 51 electrons. The krypton takes care of 36, so now we're down to showing 15. And so as we work our way, the 5s2 gets us down to 13, the 4d10 gets us down to 3, the last 3 go into the 5p3. And we can verify that, right? If we write out the whole thing. So krypton is going to give us 1s, 2s, 2p, 3s, 3p gets us to argon, 4s, 3d, 4p is going to get us to krypton, then our 5s, then our 4d, then our 5p. If we add in all of our numbers of electrons, to fill up those subshells, and then add them all up, we're going to come up with 51 electrons. So hopefully that helps, right? Again, practice both of these. There's exercises where you're practicing both. And then there's a third exercise where you're going to try to relate that to the periodic table. Spend a little time looking at that exercise and start to make that connection. It's going to be very beneficial, not only right now, but also moving forward. So that's page 3. That's the big chunk of this particular packet. Thank you so much for your time.